Okay, we are going to today we are going to talk about the stress-strain diagram, and I'm going to talk about it. Stress-strain diagram is considered to be one of the most important diagrams that you could see for any type of materials. So I'm going to talk about it in detail. So we are going to talk about something similar to this, where that we are going to make a relation between the stress and strain here, and we are going to find that it gives us a great deal of information and characteristics regarding the material under investigation. So this is why we are going to elaborate on stress-strain diagram, and we are going to address the relation between stress and strain. We're going to choose one material, which is steel, especially mild steel, because mild steel is going to find it easy to explore all the parts of the different phases of the change between stresses and strain. Okay, so we're going to find the elastic part, the yielding part, strain, hardening, nicking, fracture, and so on. It's very clear, and we are going to find we can understand it easily. Other materials we are going to study, or other materials, if you are going to study it later, you're going to find sometimes some part is not there, not very clear. Sometimes the yielding, for example, is not clear for us. There is no specific phase for yielding. For example, nicking or strain hardening is not very clear. So we are going to focus in our video for today on steel, mild steel, and we are going to study and understand the stress-strain diagram for it. Okay, let's jump into the importance of it. Stress-strain diagram for a typical structure steel in tension. Okay, a stress-strain diagram is a characteristic of the particular material being tested and conveys important information about the mechanical properties and type of behavior. This is the importance and the significance of the stress-strain diagram. So first of all, it is going to convey important information. Okay, important information about what? About the mechanical properties, because we have some mechanical properties for each material. Okay, so these mechanical properties, we want to understand it. What is going to happen in the beginning, for example, from point O to point A, for example, here, how it will behave. Okay, so it is going to be, for example, elastic part here. So if we are going to unload the material, it is going back to its original status. So this is a kind of mechanical property that we are not going to understand it unless that we draw this stress-strain diagram. And in the same time, it is going to give us and tell us the behavior in different levels. For example, at point D, we're going to find that from point D to point E, this shape of the curve is telling us that there is nicking is going to happen. If we have the bar, for example, that is under tensile stress is something like this, we're going to find that the bar is going to have some nicking here, something like here, something like this at the middle. Nicking means that contraction of the area. The cross-sectional area is decreasing with the increase, okay, or with this decreasing of the stress as well. Okay, so this is the two important things that we need to know here. Let's clear everything. So we want to know mechanical properties of the material, and number two, the type of behavior. Okay, whether it is elastic behavior here, yielding here, strain hardening here, nicking here, and then fracture at the end. Okay, so this is the significance of the stress-strain diagram. It is a characteristic of a or of the particular material being tested and conveys important information about the mechanical properties and type of behavior. Okay, now let's go and discover part by part and point by point. First of all, if we go back here, look at this point, point A. Starting from 0 here, this is where there is no stress and there is no elongation at all in the element or in the specimen, right? So starting by increasing the load and going in this direction, we're going to find the material behaves like this, that it goes in a linear way. Okay, so this is why we say that from 0 to A, we call this part the linear region, the linear region. And this linear region ends at a specific point or a particular point. We call it proportional limit. Proportional limit. Okay, the proportional limit. Okay, this proportional limit, why we call it like this? Because there is a proportional relation between stress and strain in this region. What is the meaning of proportional? It means that in this region, when we increase, its linear relation means that increase in the stress would provide increase in strain in a constant slope, using constant slope. So this is why we call it proportional. And we call this point, point A, to be proportional limit, to be the proportional limit. Linearity, the material is behaving in a linear way. Okay, later on we're going to understand that this part also, it is the elastic part. It is linear and elastic in the same time, especially for this type of material. Okay. Okay, now let's read it here. Beyond point A, okay, the proportionality between stress and strain no longer exists. So before that here, there was proportionality between stress and strain exists. After that, this proportional relation does not exist anymore. Okay, hence the stress at point A is called the proportional limit. Okay, it's called the proportional limit. It's called the proportional limit. It's called the proportional limit. The slope of the straight line from 0 to A is called modulus of elasticity. So now the slope here, if we go back here, okay, the slope of this part, the slope of the first part, this proportional relation here, the slope here, we call it the modulus of elasticity, because it is really important for different materials to know about it. Okay, so it is very important to know about this modulus of elasticity. It would give us an indication about how stress and strain behave in the first region, or in the linear region of the material, or in the linear region of the stress strain diagram. Okay, we call it modulus of elasticity because the slope has units of stress. So as you know, that it's stress here and strain on the horizontal line. So if we're going to say that Young's modulus E equals to like stress over strain, so we know well that stress, it has units of stress is like psi, for example, okay, pound per square inch. Cannot write I here, okay, psi, right? And this, the epsilon, it has no units. So the Young's modulus, we call it Young's modulus or modulus of elasticity, both are okay. So this modulus of elasticity has the same units as stress. So Young's modulus or modulus of elasticity, it has the same units as stress. Okay. At point B, now let's go to the next point, which is point B here. This is point B. It's a very small distance between A and B, but actually it starts to give us an indication of something important. So we ended here at the proportional limit at point A, and then after a while we found that there is another point called point B, and we indicate it with something called yield stress. Yield stress. Okay, so now let's go and see about this. At point B, at this point, considerable elongation with no noticeable increase in the tensile force from B to C is seen. So we are going to find that from B to C, starting at point B, there is a considerable elongation, as you can see here. The red line is almost flat and horizontal, right? This means what? There is a considerable elongation in this part, okay? The material or the specimen is being elongated. It is being stretched, okay? And this part, if you look here, it is horizontal. This means that there is no increase in the stress. Let's make it like more clear here. So as you can see, it's horizontal. There is no, it is not like this, for example. If it was like this means that there is increase in the stress in the vertical axis, but actually there is no. It is horizontal. This means what? That there is elongation in the specimen, while that there is no increase in the stress. Stress is the same. Stress is the same. Okay, so this part from B to C, we call it perfect plasticity or yielding. We call it like this, perfect plasticity or yielding. And the beginning, the onset of this behavior, the onset of this phenomenon here at point B, we call it the yield stress limit. The yield stress limit. Okay, this is the yield stress limit. So from B to C, it is the perfect plasticity or yielding. We call it perfect plasticity because it is the material is being being elongated, and it shows plastic behavior, not elastic behavior, as I'm going to talk about it later on. Elastic behavior, it was here in the linear region, where that whenever that we are going to unload the specimen, then the material or the specimen is going to takes back its original shape. But here, this is the part where that perfect plasticity exists, where that the material is going to be in a perfect plastic form. Okay, anything that is going to be deformed here, a great deal of it is not going to be recovered again. Okay, so this phenomenon is known as yielding. As we said, this part here, it is yielding. At the start of it, at point B, is yielding. Yielding of the material. And point B is called yield point. So we start with this, point B, yield point. The corresponding stress is known as yield stress. The corresponding stress here, we call it yield stress. We call it yield stress of the steel. Okay, or talking about the steel specimen. Okay. In the region from B to C, the material becomes perfectly plastic, which means that it deforms without an increase in the applied load. That's the meaning of perfect plastic. So if I ask you what is the definition of perfectly plastic region for mild steel, then the meaning here, or the definition, or the understanding of this perfectly plastic phenomenon is, it is the stage, okay, where the specimen or the material deforms without an increase in the applied load. Okay, the material or the specimen deforms without an increase in the applied load. Okay, let's jump to the next part. Let's go to the next part after that, which is strain hardening. We reached now point C. We understood now what is the meaning of linear region, and we understood that there is a proportional relation between stress and strain in this region, which is the linear region. As you can see, the relation is linear. After that, from point B, from point A to point B, the slope is going to change, and we said that there is a start of yielding of the material from B to C. And we said that the next part, or the next phase, what we call it perfectly or perfect plastic region or yielding. And then at the end of this part, we said that the start is going to be from point C onward till point D. And we are going to give this phase a name called strain hardening. Strain hardening. So during strain hardening, the material undergoes change in its crystalline structure. So that's the main, this is the most important word here, crystalline structure. The material itself is going to change. The crystalline structure of the material is going to be changed, resulting in increased resistance. That's very important. Resulting in increased resistance of the material to further deformation. So all of a sudden, after having the yielding as a flat line between B to C, all of a sudden we found that starting from C, there is something happened in the material. The crystallines of the material, the crystals of the crystalline structure of the material is going to be changed, and resulting in increased resistance of the material to further deformation. So we're going to find something like this, as you can see here. What is the meaning of this slope here? The slope here means that the material or the specimen is showing resistance, okay, and still there is some elongation as well. The strain is increasing here, and we call this strain hardening. So if I ask you what is the main reason for strain hardening, the answer simply is going to be due to the change in crystalline structure. This results in increased resistance of the material to further deformation. Okay, so that's the key word here. Elongation of the test specimen in this region requires an increase in the tensile load. So this elongation that is going to take place here requires what? Requires an increase in the tensile load, and therefore the stress-strain diagram has a positive slope from C to D. So it is, as you can see here, from C to D it is positive slope. This is positive, okay? If it was negative, for example, it was something like this. Okay, so we are having positive slope, not negative slope. Why? Because the elongation of the test specimen in this region requires an increase in the tensile load. The material or the specimen needs more loads. Okay, so this means that the stresses needs to be increased. The load is going to be increased, and the cross-sectional area is going to be constant, right? So we are going to have what? Increase in the stress itself. And this is what is happening here. Positive. Okay, so if I ask you another question and say that why the slope from point C, let's clear it out here, from point C to point D, why the slope is positive? Okay, so the answer is because the elongation of the test specimen in this region requires what? An increase in the tensile load. We need increase in the tensile load. And when we increase the tensile load, definitely the stress will increase as well. Because the cross-sectional area of the specimen is the same, right? So therefore the stress-strain diagram has a positive slope from C to D. Okay, it requires more because other materials, sometimes other materials or even other members, if we're talking about stress-strain curve for some elements or force deformation for some elements, sometimes we can experience something like this, which is the slope is going to be negative. So what is the reason for this negative slope? The elongation, still there is some elongation, but the point is the elongation of the specimen in this region requires not an increase in the tensile load. Otherwise it should be decrease in the tensile load, so it would give us negative sloping here, and therefore the stress-strain diagram has it should be, in this case it will be negative if we're talking about negative slope from C to D. Okay, so now we understood well what is the meaning of strain hardening. Let's go after that at point D and look onward. At point D, there is something, the load eventually reaches its maximum. As you can see here, we are reaching the maximum of everything for us. So this part, we call it the ultimate stress. This part, we call it the ultimate stress. And the corresponding stress at point D is called ultimate stress. Ultimate stress means what? The crystalline structure of the material could not provide any further resistance for the load, or cannot show more resistance. Okay, So that's the meaning of the point D here, that it reaches the maximum here. Okay, the material could not provide any strain hardening anymore. This is due to, as we said, the crystalline structure of the material. After that, at point D, there is something would happen, start of something that is going to happen. You can find it in the videos that I'm going to. So we're going to find something, we call it nicking. Sorry for drawing by, okay, I hope that this is, okay, this is not very good, but anyway, let's clean it up. And so if we say this is the specimen here, and then there is something like this, and here's something like this. For example, this part here, what we call it the nicking. Okay, start of the nicking. What is happening here at point D? The specimen itself, the specimen starts to have some contraction at the middle. So the area that is resisting the applied force, if we have applied force here and here, for example, so the force, the area that is being applied, the area that is used for the applied force is going to decrease. So starting from here, we are going to find what we call it nicking. From after point D, we're going to find what we call it nicking. Okay, after reaching the maximum, we are going to find that the specimen is like as if it's dropping the stress, because of what will happen in this phase is nicking. Let's start to understand what is the meaning of nicking and how we can reach the ultimate failure. Further stretching of the bar is usually accompanied by a reduction in the load. So yes, that's right, reduction in the load. And fracture finally occurs at point E. This is the fracture here. So here, this is what will happening here. It is nicking. Nicking means that contraction of the area in the middle of the specimen, and the decrease in the area that is resisting the stresses, or resisting the loads. So we are going to find that there is some nicking here is going to happen, and the element is going to reach fracture. I think that you can find this easily from the videos that already I have like showed before. You are going to find that when the element is reaching this nicking stage that we were talking about, so okay, so this is here and this is the nicking stage. So at this stage here, fracture would take place at the smallest part here. This is what we call it fracture at the end. Okay, after nicking, and this part, as we said before, it is nicking. Okay, now the last, maybe we can mention about some names here that we usually use, which is the yield stress and ultimate stress. The yield stress and ultimate stress of material are also called yield strength and ultimate strength. So they are like synonyms, okay? They are interchangeable. The word stress is okay, so you can say yield stress or yield strength, and you can say ultimate stress or ultimate strength. They are the same, okay? So they are the same, no problem at all in using them as they are strengths or strengths. The word strength, whenever we use the word strengths in general, in mechanics of material, is a general term that refers to the capacity of a structure to resist loading. So whenever we say, generally, whenever we use the word strength, it means that the capacity of a structure or an element, okay, or this specific type of material, for example, okay. So that's the issue here. For instance, the yield strength of a beam is the magnitude of the load required to cause yielding in the beam. And the ultimate strength of a truss is the maximum load it can support, that is the failure load. So the word strength always should be linked in your mind with the meaning of failure load or capacity. That's the meaning of strength in general. Okay, so whenever that I say what is the strength of this material, for example, it means that the ultimate stress here. Okay, commonly this is the meaning. If I say what is the yield strength, it is this one, yield stress here. Okay, but if I say only strength, what is the strength of this material? Well, it is the maximum resistance that it could it should show for us. Okay, and this is the last thing that maybe I'm going to talk about, which is the lateral contraction. When a test specimen is stretched, this is the test specimen that we usually have. This is the region of nicking, and this is where fracture is going to happen. As we said, this is where fracture is going to happen. This is the part here that we're talking about. So this is the region of fracture, as you can see, and here the material is going to be torn apart. When a test specimen is stretched, lateral contraction occurs, as previously mentioned. The resulting decrease in cross-sectional area is too small to have a noticeable effect on the calculated values of the stresses up to about point C. So until here, until this point C, this is the stress strain curve is okay for us. Area that we are dealing with, we call it the total area, or the area without contraction. After that, actually the area is going to decrease. There is contraction here, but commonly engineering wise, we are neglecting the contraction and we are saying that we are going to use the whole cross section. I'm going to talk about this in the next video, but anyway, until this part, until point C, there is no decrease in the area. So we are dealing with the whole area of the specimen. Okay, the whole area of the specimen here, for example. But when we reach point C, we are going to find that the area of the cross section is going to be changed. So we need to take care of this because there is some change in the area, and the stress strain, as you know, that the stress here is going to be equal force over the area. Area here starting from point C is going to be smaller than what we are dealing with. So anyway, this is what we are going to talk about in the next video, which is going to be stress strain diagram 2. Okay, so let's recap what I have said here for this video. I was talking about stress strain diagram, and I mentioned about the different phases that you are going to find on this diagram. We said that we have linear region, and up until point A, which we call it proportional limit. After that, there is a decline in the slope between point A and point B, where that the yield stress of the material starts. After point B, there is a phenomenon called perfect plasticity occurs, or we call it yielding. From point B to point C, this is the perfect plasticity area. After that, we are going to find another behavior that is going to take place. We call it strain hardening behavior, where that the crystalline structure of the material contributes well to increase the resistance in terms of stress with the elongation here of the strain. After that, we mentioned that there is positive slope because sometimes we can have negative slope, and we said that the reason for this positive slope, that the elongation that is going to take place requires more load in the specimen. So the stress is going to increase and we need positive sloping. After that, we mentioned that we are going to reach point D, where that it is designated with the ultimate strength or ultimate stress of the material. And after that, we are going to find that the material is going to go into another phase called nicking, and it goes down from point D to point E, and at the end we're going to find fracture will take place. So this fracture is going to manifest itself, as I said, in nicking and then fracture at the middle. This is the all about today's video. Thank you, and see you in the next one.